clustering K means algorithm segment as clustering. Segment as clustering. Segment as clustering. Pixels are points in high dimensional space. Color 3D, color plus location 5D. Cluster pixel into segments. Here, cluster pixels into segments. 3D. Color 3 dimension, color plus location 5 dimension. This is 1, 2, 3. 1, 2, 3, 4, 5. Color plus. Here color 2 dimension. Okay. Clustering K means algorithm randomly initialize the cluster centers C1 to Ck. Given cluster centers, determine points in each cluster. For each point P, find the closest Ci. Put P into cluster I. Given points in each cluster, solve for Ci. Set Ci to be mean of points in cluster I. If I see I have changed, repeat step 2. Properties, this is the algorithm for clustering K means. Properties will always converge to some solution. Can be a local minimum. Does not always find the global minimum of objective function. Properties will always converge to some solution, can be a local minimum, does not always find the global minimum of objective function. Summation of I equal to 1 to k x for all Ci summation double mod Cx minus Ci square. Clustering K means this is K2, K equal to 2, this is K equal to 3. Clustering K means visual segment with the average color. K means pro, extremely simple, efficient, con, hard concentration clusters, cannot handle non-spherical clusters. Gaussian mixer model represent data distribution as mixture of multivariate Gaussians. P of x equal to summation over I equal to 1 to k into k pi I dot pdf into x comma mu I comma epsilon I. Here x y. How do we actually fit this distribution? X. Okay. So expectation maximization EM. Goal, find parameters theta for GMMS pi I mu I summation I that maximize the likelihood function. P of data comma that theta comma theta equal to uh, pi overall I equal to 1 to n p of x xi comma theta. Approach E step. Given current parameters, compute ownership of each point. M step. This is the E step. Second one is the M step. Given ownership probabilities, update parameters to maximize likelihood to function. Repeat until convergence. Clustering expectation maximization EM. GMS Pro still fairly simple and efficient. More model complex distributions. Model more complex distributions. Con. Need to know number of components in advance. Hard to know unless you are looking the data yourself. Clustering mean shifting. Clustering mean shifting. -4, -2, 0, 2, 4, 6, 8, 0, 2, 4, 6, 8, 10, 12. Initialize random C and window W. Calculate the center of gravity, the mean of W 1 by mod W summation over x for all W x. Can generalize the arbitrary windows kernels, shift the search window to the mean. Repeat step 2 until convergence, only parameter window size. Mean shifting. Region of interest. Center of mass. This is the region of interest. Region of interest. Center of mass. Center of mass. Region of interest. Mean shift vector. This is the mean shift vector. Mean shift. Region of interest. Center of mass. Mean shift. Here. Mean shift. Region of interest. Center of mass. Mean shift. Mean shift vector. Region of interest, center of mass, region of interest, center of mass. Clustering, mean shift. Cluster all data points in the attraction basin of a mode. Cluster all data points in the attraction basis of a mode. Attraction basin, the region for which all trajectories lead to the same mode. Here, lead to the same mode. Attraction basin, all data points in the attraction basin of mode. Okay, here. Mean shift for segmentation. Mean features, color gradients, texture, etc. Find features, color gradients, texture, etc. Initialize windows at individual pixel locations. Perform mean shift for each window until convergence. Merge windows that end up near the same peak or mode. Okay. Mean shift for segmentation. Mean shift for segmentation. Mean shift pro, no number of clusters assumption, handle unusual distributions simply. Con, choice of window size, can be somewhat expensive. Okay. Clustering Pro generally simple can handle most data distributions with sufficient effort. Hard to capture global structure, performance is limited by simplicity. Outline graph-based segmentation, general properties, spectral clustering, minimum cuts, mean cuts, normalized cuts. Images as graphs P, WPQ, Q, okay, WPQ. Node here, this is W. So node vertex for every pixel. Okay. Affinity weight WPQ for each edge. WQ measures similarity. Similarity measures. Similarity is inversely proportional to difference. Similarity is inversely proportional to difference in color and position. Images as graphs. Which edge is included? Which edge is included? Fully connected. Captures all pairwise similarities infeasible for most images. Neighboring pixels very fast to compute. Only captures very local interactions. Local neighborhood. Reasonably fast graph. Still very sparse. Good trade-off. Measuring affinity. In general, AFF of x comma y equal to expectation of minus 1 by 2 sigma square d mod f of x minus f of y whole square double mod. Examples: distance f of x, location of x, intensity f of x, intensity of x, color f of x, color of x, texture f of x equal to filter band x. Note can also modify distance metric. Measuring affinity. Distance f of x equal to location x. Okay. Here. Measuring affinity. Intensity f of x equal to intensity of x. Intensity of x. Measuring affinity. Measuring affinity. Color f of x equal to color x. Color x. Measuring affinity. Texture f of x equal to filter band of x. Segmentation as graph cuts. Segmentation as graph cuts. A, B, C. Here, 3 dot. This side, this side, this side, this side. Straightforward. In B, like this. C is not specified here for C. Then break graph into segments, delete links that cross between segments. Easier to break links that have low similarity, low weight. Similar pixels should be in the same segments. Dissimilar pixels should be in different segments. Graph cut with the eigenvalues. Given affinity matrix W, the goal extract a single good cluster V of I. Score for point I for cluster V, maximum V power T W V, ST